So I want to do an example. It's number 12 in the book. So we have a parallelogram that I've labeled A, B, C, D, and gone ahead and drawn it all with the lines that are represented there. And what we want to do is we want to create a transformation from a simpler object, like maybe a rectangle of some sort, to this object that is we're given. And T inverse will be the pullback transformation from the more complicated one to the less complicated one. We're going to call this one R, and the book calls this one S. The less complicated one that we're going to actually take the integral over is going to be S. The more complicated one is the one that we are given that we're going to try to avoid at all costs. So there's an area difference here that we have to take into account, and this example shows you what you have to do in order to even get to that point. So what I'm going to do now is I'm going to find the equations for AB, AD, BC, and CD. All right, so I'm going to come back and do that. So here I am. What I've done is I've taken all the points A, B, C, and D, and I've found the equations of the lines that connect them. So if you want to pause the video and see how I might have gotten these, see if you can get these same answers. What I want to do is convert this parallelogram to some sort of rectangle that has sides that are parallel to the X and Y axes, or it's going to be U and V axes actually. And so if they're parallel, I'm doing this with a parallelogram. If it were a circle, this may not be as easy. I might have to, or an ellipse. If it were an ellipse and I want to convert it to a circle, then that's a different process. But since the sides of this parallelogram are all lines, I can convert it to something in which the sides are all lines, and those lines are going to be parallel to the axes. With that said, if the lines are parallel to the axes, then U and V are going to be constants, and I can convert these lines so that they're equal to a constant. Like for example, if you look, y equals 3/4 x, I can multiply through by 4 and then move the 3 over. So that would be 4y minus 3x equals 0. If I look at the next line, I can multiply through by 4, just do some scratch paper, 4 y equals 3x plus 10, and I get 4y minus 3x equals 10. So you see how the left side is y's and x's, and the right side is 0 and 10. These are constants. So what I've done is I've taken two of the lines that are parallel, and I have made them look the same on the left side. Now I'm going to take the other two. This will become more obvious in a second while I'm doing this. I'm going to take the other two, multiply by 2 on both sides. See, multiply by 2 on both sides. And so I get 2y plus x equals 0. All right. And then on the other one, I multiply by 2 on both sides. And you get 2y plus x equals 10. Yeah. So I get 2y plus x equals 10. So what I can do here is I can let, for example, u equal 4y minus 3x, and I can let v equal 2y plus x. And in this way, if you look above, u is between 0 and 10, and v is between 0 and 10. Now, that doesn't always happen. It just depends on how you work this stuff, all right? And so now I have, I'll draw it down here, a nice rectangle where this is 10, this is 10 here, I have a nice rectangle, actually a square, that I can integrate over instead of that gross parallelogram that I would have to integrate over. Integrating over this parallelogram, it would not be fun, you see. Try think about it. All right, so I have the u-axis, and I have the v-axis, and my transformation goes from simple to more complicated, that's t, and more complicated back to simple, that would be t inverse. The first one, let's see, from the inverse one, this here, this is t inverse because it takes x and y values and it converts them to u and v values. Now the job is to find out what t is. What is t? So what you do is you solve for x and y in the u and v equation, and you get t from that. So before we do that, though, let's just see what's happening here. Let's see what goes to what. So if you notice, u equals 4y minus 3x. So when u is 0, that is right here. When u is 0, that's right here. And that corresponds to where AB is. AB. Because that's u is 0, because u is 4y minus 3x. All right? So now whenever u is 10, that's up top here. U is 10 is here. So that corresponds to DC. Because when u is 10, we've got DC going on. That's the DC line. So this would be the DC line, and then this would be the AB line on the left. And now when V is 0, that's right there, that's AD. V is 0 is on the U axis, so this would be AD. And then when V is 10, that would be BC. V is 10. This would be BC, yeah, BC, like that. And so that's where each one goes. All right, now for T. So what is that equal? What is T equal? So what you do is you take your UV equations and you solve for X and Y. So I'm going to rewrite them and come back. All right, so if I take U 4y minus 3x and I multiply V times -2, and I'm trying to get rid of the y's. I'm solving for x and y in the u and v equations here. So it's kind of like solving simultaneously. So I'll multiply by -2 on the bottom, and I add u minus 2v equals -5x. So this becomes x equals -1/5 x, -1/5 times u minus 2v, or x equals -1/5 u plus 2/5 v. All right, so that's x. Now, if I take those two equations and I want to get rid of the x now, I multiply by 3 on the bottom. So this is u equals 4y minus 3x. 3v equals 6y plus 3x. Add them, and I get u plus 3v equals 10y. X's cancel. So I get y equals 1/10 times u plus 3v, or y equals 1/10 u plus 3/10 v. So this is the y and the x, and that is going to be our t. So going back to this, let me rewrite it. So we have t, it's black. We have t as x equals negative 1 over 5 u plus 2 over 5 v, and then y equals 1 over 10 u plus 3 over 10 v. All right, so in the context of this, t, if you look at t goes from the uv to the x's, and yeah, we're taking u's and v's, and we're converting to x's and y's. So that is our transformation from the simple to the more complex one. The reason we do this is because of what's called the Jacobian. And the Jacobian is going to come into play in just a minute. Well, let's do it now. Let's do it now. All right. So the Jacobian is going to be taking care of that little change in area. So the Jacobian is defined as the following. It's the determinant of this matrix. It's the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. So I usually write this as determinant. Remember, you can write as straight up and down bars instead of the parentheses. X u, x v, y u, y v. Like that. This is a v. And so it'll be x u y v minus x v y u, like this. And we're going to take the absolute value of this later. So when we look at the matrix, the Jacobian matrix that we have here, what we get is x sub u would be negative 1 over 5, x sub v would be 2/5, y sub u would be 1/10, and y sub v would be 3/10. When you do the determinant of this matrix, you get negative 3 over 15, or 50, minus 2 over 50, which is negative 5 over 50, which is negative 1/10. And now you take the absolute value of it, and we get 1/10 out of that. So a little change in area is 1/10. All right, so the change in area from the R to the S is 1/10. So let me show you why that's true. The S area, the area of S, is 10 times 10, which is 100. Now I'm going to use the idea of vectors to show you how we can find the area of R and show you that that's 1/10 of S. And that's what our Jacobian little piece is going to take care of whenever we convert from integration over R to integration over S. So if you take AB as a vector, AB as a vector, AB would be 4, 3. And then AD as a vector would be, well, let's say 4, 3, 0, because I'm going to do the cross product here. AD as a vector would be negative 2, 1. Negative 2, 1, 0. Now the cross product of these two, will be 0, 0, and then 4 minus a minus 6, so 4 plus 6 would be 10. 10. And so the area of R is the magnitude of this cross product, and that would be 10. So R, the area of R is 10, the area of S was 100, and so if you take 100 and multiply times this Jacobian, which is 1/10, you get 10 out of that. So to go from one to the other, you multiply by 1/10. And that's where this Jacobian piece comes in. So what we're going to do is we're going to do the following. We're going to take the double integral over R, which is our parallelogram, of some function acting in the z direction, dA, and we're going to convert that to an integral over s. This is uv, r is x and y, and we're going to convert that, f of uv, we're going to multiply times the absolute value of the Jacobian and then dA. And this dA here will be du dv or dv du. This dA here will be dx dy or dy dx, your choice. This u and v here will be the transformation that we got before. So u equals and then v equals some function of x and y and some function of x and y here, h of x, y. That's our transformation. That's why we had to get this guy right here. That's our inverse transformation, excuse me. Sorry, inverse transformation. Okay, so here's the deal. You take a more complicated, you take an integral that's being integrated over a fairly complicated object. You convert it to an integral that's where you integrate over a less complicated object, but you have to multiply by an area element in there. It's not always easy to find that area element by hand. See, it was pretty easy to find the area element by hand over here, but that's not always the case, and you don't even have to do that. Jacobian's pretty easy to find. All right, so that's one example.